Here.
Okay.
Good afternoon, sir.
Good afternoon, Digwas. Good afternoon, Professor Costa.
Good afternoon.
Sanjeev, when you are going
Professor Sharma is the chairman of IEEE APS chapter Jaipur. I think so. Formally, we have to start now. Hello, sir. Aman, sir. Are you
Okay, I can start.
Yeah. No, just very good afternoon to all the participants. I, Dr. Sanjeev, welcome you to the second day and the second session of the International Workshop of Metamaterials and its applications. Today, we are having Professor M.M. Sharma, who is the chair of APS chapter Jaipur, Dr. J.K. Digwal, who is the principal of Government Women Engineering College, Ajmer, as well as we are our speaker for today is Professor Filippo Costa from Italy, University of PISA, Italy, and we are having the many of the faculty members, research scholars, PG students, and the industry persons as an audience. Now I request Professor M. Sharma to say a few words.
Are you asking to me, Sanjeev?
Yes, sir.
Sanjeev?
Yes, sir. Yes, sir. I am asking to you a few words.
Very good morning to Dr. Filippo Costa. So there is a good morning only. and a very good afternoon to our Indian friends, our participants. On behalf of IEEE APS chapter, Delhi section, Jaipur chapter, IEEE Rajasthan subsection, Government Women's Engineering College, Ajmer, India, and Department of Electronics and Communication Engineering, Malviya National Institute of Technology, Jaipur, Rajasthan. I invite to all the participants here in this beautiful series of Metamaterials workshop and webinar here. Dr. Costa is a very good and propagation. He is continuously awarded for 2015-2018 outstanding reviewer. So in the last, I will ask him to just give some tips about the review the technical paper, or to just give some tips how to write about the technical things that we can avoid. And also the outstanding young scientist award. He also got the young scientist award also, and he has many published papers. He has a good contribution of the papers on the metamaterials, metasurfaces, and its application. And his area is he is also interested in the characterization of metamaterials. Okay, so I welcome Dr. Filippo Costa in this webinar along with all the participants here. Thank you.
Thank you. Thank you.
संजीव आपकी आवाज नहीं आ रही है.
Okay, I request Professor J.K. Digman to say a few words about the workshop.
Thank you, Sanjeev. Good afternoon, sir. Good afternoon, Professor Costa.
Good afternoon.
Good evening, dear. Good morning, sir. Good morning. On behalf of Government Mahila Engineering College, Ajmer, I heartily welcome Professor Costa in this 5-day metamaterial workshop. And our Guru, Professor M.M. Sharma also is there. I also welcome Professor M.M. Sharma in this occasion, sir.
Good afternoon, Iqbal sir.
Thank you, sir. Need your blessings always. And so I heartily I welcome again the speakers and the participants who are joining this workshop and learning the things about the metamaterial. Thank you. Thank you, Sanjeev.
Okay. Okay, I am reading out the some brief biodata of the Professor Costa. That is, Professor Costa received the MSc degree in telecommunication engineering and the PhD degree in applied electromagnetism from the University of PISA, Italy, in 2006 and 2010, respectively. He is an assistant professor in the University of Pisa. In 2009, he was a researcher in the Department of Science and Engineering at the University of Technology, EKK, now Aalto University in Finland. During the period 2000 to 2017, he was several times a short-term visiting researcher in Nobel Institute of Technology, Valence, France, and at University Robria and Vercelli, Spain. His research interests include metamaterial, metasurface, antennas, electromagnetic characterization of materials, and radio frequency identification, that is RFID. He has served as associate editor in the journals IEEE Sensor Letters, Electronics and Sensors. In 2015, 2016, 2017, and 2018 and 19, he was selected among the outstanding reviewers of the journal IEEE Transaction on Antennas and Propagation. In 2017 and 2018, he was selected among the outstanding reviewers of the journal IEEE Antennas and Wireless Propagation Letters. He was the recipient of Young Scientist Award of the URSI International Symposium on Electromagnetic Theory, URSI January and URSI 2013, 2014, and 2015 respectively. He is also a senior member of IEEE. So I request Professor Costa to start his talk. Now floor is yours.
Okay. Thank you. Okay, can you hear me?
Yeah, you're audible.
Okay. Okay. Thank you. Okay, this presentation is about is a general overview, let's say, a broad view of metamaterials. It's not on a specific topic. There are many specific topics in metamaterials because it's very broad and a multidisciplinary topic. I try to present the topic from a high-level point of view in order to help those people who are just at the beginning, at least, of this topic to orient themselves and help them to understand a little bit more about this this topic of research. I start with this slide, which is just a classification of engineered material, which is maybe a broad classification of the with respect to metamaterials. Is those materials who are engineered, which can be engineered from the point of view of electromagnetic waves. So we can interact with electromagnetic waves by using ordinary materials, which are conductors, dielectrics, magnetic material, chiral materials, and those materials are usually available in nature, and we can take them and play with them in order to shape or influence the behavior of electromagnetic waves in some ways. But we can even wield some material in a lab in order to maybe obtain some non-ordinary properties, or maybe some different properties with respect to those available with ordinary materials. For an example are the mixtures. Mixtures can be obtained by mixing some different materials in the shape of let's say spherical particle or other shapes, and put together with other materials, and we can obtain some different material with respect to their components. The third classification of the material is the metamaterials. Metamaterials are obtained not with just plastic material or dielectric materials, but also by including some resonant inclusions with metallic materials. So we design some resonant inclusion, and we obtain some interesting resonant properties or non-resonant properties, and we can achieve some interesting features from the material, which could help in many applications. The last category is maybe the photonic crystal, which is another broad topic which often involve light or electromagnetic waves at very high frequency or very short wavelengths. And there is a big difference between metamaterial and photonic crystal. The main difference is that photonic crystal are only dielectric structures, and the second difference is about the periodicity, no, of the periodic structure. They are both periodic structures, but photonic crystals are in a scale which is much larger than metamaterials. With the next slide, we can see a little bit better the difference. If we take a sort of axis, which represents the sides of the periodicity of a unit cell, we can have that the ordinary materials have features, no, which are in the order of very small fractions of the wavelength which interact with the material. With mixtures, the wavelength of the material interacting with the mixture is much larger again from with respect to the feature of the material, which we can average the properties of the material in order to have a sort of homogeneous material. The same we want to do with the metamaterials. The objective of this topic is to achieve, let's say, a material which hopefully can behave as another block of homogeneous material with special properties. In order to do that, it is necessary that the inclusion inside of the metamaterial, no? the periodic inclusion, which is much smaller than the wavelength. The maximum that could reach is the half wavelength, not more. On the opposite is the photonic crystal. In photonic crystal, you have the properties, the photonic band gap, and the particular properties of the photonic crystal instead obtained thanks to the lattice, no? Because the lattice is the grid in which you repeat your unit cell in order to form this periodic arrangement of particles. And in this case, the lattice has a period which is larger than the wavelength. And the period larger than the wavelength give properties which are unconventional, like band gap or other interesting properties, which are obtained with the photonic crystal, which are mainly used for confinating light. In this case, we talk about Bragg scattering. Okay, let's see a little bit more in detail mixtures. Mixtures, as we said, are the materials in which you can see like a two-phase material in which you put some inclusion in a host material, which is called hosting medium. This inclusion can be of spherical shapes independently. The size of this shape is not very important if the size is very small to the wavelength. The important thing is the dipole moment introduced by this inclusion. You can see the effective properties of the material as a summation of the dipole moments of these inclusions, which is proportional to the polarizability of the material and to the external electric field. So the polarization of the material introduced by this dipole moment, the average polarization, gives effective properties, and an electromagnetic wave which invests this material is not able to understand what is included, which is the shape of different material inside, but feels like an average properties, which is called the epsilon effective epsilon. No? Okay, usually these materials are described with mixing rules. The most important probably formula for this material is the so-called Maxwell-Garnett formula. Is derived also in, sometimes it's called Clausius-Mozotti if it's written in different form. But the important thing is that we are able to express the effective permittivity of the material, no? Where this inclusion with the internal epsilon are put inside with an effective properties. The effective properties are clearly influenced by the internal permittivity of the inclusion and the external permittivity of the hosting medium. We define a filling factor, which is called F. If this filling factor goes to 0, so you have no inclusion inside, the effective epsilon is the epsilon of the hosting material, epsilon E. If you have your material filled completely of this inclusion, clearly you have that effective epsilon is equal to the internal epsilon. If you have this F factor, which is an average medium value, you have a sort. You can select an effective permittivity depending on the inclusion, or how many inclusion you put inside. This is very interesting to create material with effective epsilon which are not available, no? For a certain application. This is a very good paper to study this topic. Is a good review from Ari Sivula from University of Finland, Helsinki. If you plot, let's say, this formula, you obtain something like that. Basically, if you have you can plot the contrast as a function of the contrast. In a y-x axis, you have the volume fraction F. In the y-axis, you have the effective permittivity. You can plot for different contrasts. So if you have more contrast between the inclusion and the hosting medium, let's say the inclusion has an epsilon, which is in the order of 100 with respect to the external medium, you can achieve, depending on the volume fraction, the permittivity you desire in your mixture. And if you have a smaller contrast, for sure you can achieve lower permittivities. Clearly, this is valid for spherical shapes. If you select other type of inclusion shapes, you can modify your theory, and you can. This is a comparison between spherical needle shape inclusion and discs. If you, in this case, the plot is given as a function of a inclusion volume fraction F, but in the y-axis there is not the effective epsilon in this case, but it is parameter susceptibility ratio, which is nothing more than this ratio, which means that if you have that your effective epsilon is equal to epsilon external, so they are identical, this quantity goes to 0, so you are here. This is the case of your material susceptibility ratio is 0, means that you have an external permittivity. The mixture has the same permittivity of the external medium. On the contrary, if the effective permittivity is equal to epsilon E, the internal permittivity, you have that this fraction goes to 1, and if you are here in the plot. But in the they behaves, the different particle determine different behavior in the plot, because if you see, for instance, if you have a small contrast, all the shape of the particle is not important. So if you select epsilon E over epsilon I over epsilon E equal to 2, the shape is not relevant. But if the inclusion contrast is very high, if you use spherical particles, actually, even if you fill a lot your mixture with particles of spherical shapes, you are not able to achieve a very high susceptibility ratio and therefore very high epsilon effective error. On the contrary, if you use discs, you are able to obtain a very high effective epsilon, even if you fill your material. So you have much more degrees of freedom, or let's say much more choices on the permittivity, if you need to obtain a very high one. But anyway, you can define some bonds. For instance, if you have this plot with this volume fraction and effective permittivity, you can define a higher bond and a lower bond. Depending on the shape or other properties, you can achieve effective epsilon, which goes inside this inside this area. You are not able to synthesize material with the properties outside from this area. These are the upper bound and the lower bound of the effective permittivity you can achieve with your material. And the precise point which you feel you fall depends on the shapes of the particle and your specific model. Okay, I want to just summarize instead the metamaterial in some words. I will try to do this, which is the second category of engineered material we've seen. Metamaterials, as we said, is a material. No, I taken the definition from Wikipedia in this case. Is a metamaterial. The word derived from the Greek, no? Meta, and meaning means beyond. So it means beyond the ordinary material. The idea is to find material by engineering them with properties which are not available with the ordinary materials, and they are usually made with assemblies of elements arranged usually in a periodic configuration, in a three-dimensional periodic configuration, and the scale of the repetition period A, as defined in this figure, is much smaller, as we already said, from the wavelength. So the wavelength is much larger than A. If this condition is verified, you can see your material as a block of a certain homogeneous material with a certain effective epsilon and effective mu. This is the idea. So the idea is similar to the mixtures. But in this case, it is more complicated because if we use metallic particles with resonant properties, as we will see, we obtain some nonlinear phenomena which are maybe difficult to handle, to derive an epsilon which is independent on the angle or on the frequency. Anyway, the properties of this material will depend clearly on the shape, on the geometry, on the size, orientation, arrangement of this small particle which are used to generate the effective properties. We want to use metamaterials usually for, let's say, interact with waves in a clever way. We want to block, if you eventually block waves, let's say, if we need to stop the propagation of a certain electromagnetic wave. Maybe we want to absorb the wave if it is needed from a specific application. We can enhance a certain field in a certain region of a space. We could need to bend waves, no? in a certain guided device, or achieve properties which are not usually possible with the ordinary material. Okay, let's see a little bit the history of this material very shortly. As you probably know, no? The seminal paper about this topic has been presented by Victor Veselago, which is a Russian professor, who was a Russian professor, and he asked himself this question: what happens in a material when both electric permittivity and magnetic permeability are negative? So it was, let's say, a very strange, weird question, because usually one thinks that it's not possible to achieve at the same time epsilon negative and mu negative in a material. But he just theoretically asked himself this question, and he wrote down Maxwell equation, putting inside the negative mu. So you change, just say, change the sign inside this equation, the Maxwell equation. If you change the sign to mu, is equivalent to changing the sign to H and E. No? So you can change the sign of E, just shift your minus sign to this R of the equation. So at the end, if you put the negative sign to H and E, you obtain this left-handed system. So K, E, and H are now left-handed. So you should not use your right hand to define the typical term. No? E go of a plane wave. So E goes to H, and K in your tomb is the propagation of the wave direction. But in this case, you should use your left hand, and if you have your electric field going to the H field, you define the propagation of the electromagnetic wave with the negative direction with respect to the right-handed system. So this is what is theoretically expected. If we take the Snell law, the conventional Snell law, which is very well known from basic courses of physics, you can define that at an interface between a medium 1 and medium 2, you can define the direction of the angle of propagation in the medium 2 by imposing the momentum conservation of the tangential component of the K vector. No? If you have a certain wave with K1 in certain incident angle, you have the tangential component of the K vector, which is defined as K1 sin theta 1. In the medium 2, you have the K2, so the propagation of the wave in medium 2 will follow this direction theta 2 in order to satisfy that the tangential component of your K vector, so that is defined as K2 sin theta 2, is equal to the tangential component of the K in medium 1. So you can impose this equation, and if you simplify with respect to K0, you obtain the standard Snell law. No? So N1 sin theta 1 is equal to N2 sin theta 2, where N is the refraction index in the material. Okay, if we use this concept, and we have in the double positive medium, so ordinary medium with N2 larger than 0, you have usually that the theta 2 is equal to a sine, so the inverse of sine function N1 over N2 multiplied by sine of the angle, incident angle. This will define a positive angle, theta 2, and you have the propagation as usual. In a denser medium, you see this band of the electromagnetic wave. But what would happen if you have N2 lower than 0? No? If you have N2 lower than 0, in this equation, you put a negative value of N2, and the theta 2 angle will be negative. No? It means that you have your wave is not just refracted or bent in the second medium, but you see this this effect of the wave, which is going in the negative direction. So it's called the negative refraction. There is another particular properties, as you see, because in order to have the conservation of the momentum at the interface, this vector should be in the same direction, this tangential vector. It means that your wave in the medium 2 should be counter-propagating. So the K vector is in this direction, but the wave is propagating, so in time, the wave is moving towards the interface, is not going from the interface, but is moving toward the interface. This is a strange effect which is seen in this refraction from an ordinary material and a metamaterial in the sense of negative refraction, refraction index material. How we can achieve these properties? No, these properties scientists are used to understand how to achieve these properties. So we should excite a dipole moment in the material in order to have a permittivity, strange negative permittivity. So the ingredient used to obtain negative permittivity is a wire, is an array of wires. The other ingredient used for obtaining magnetic negative properties is a loop. So we need magnetic dipole moments. Magnetic dipole moments are usually obtained with current electrons rotating in a circle. So if you have electron forming a loop, you have a magnetic dipole moment towards the normal with respect to this loop. So you have the field, the magnetic field should couple with this loop. Okay, these are the current. So if we deal with the wire medium, actually is not a new topic. If you go in the literature, if you go back in the literature, you find probably the first paper on this topic is from John Brown, and has been published in 1952 in the IEEE journal, and he just studied an array of wires, no? Formed by these wires, and he just studied as with this equivalent circuit in which the wave is can be represented as a current and voltage interacting with this shunt connection of loads at a certain distance b, and a certain distance is represented by a short piece of transmission line. The loads are clearly inductive because the current flowing in the wires gives you an inductive behavior. The split ring resonator has been firstly used by Pendry in 1999, and he wrote this paper, which is quite popular, and he reported also the properties of different shapes of this magnetic inclusion, which are, let's say, able to, if used in a periodic fashion, as in this case, with the magnetic field coupling with this current loop, the period, as usual, A is much smaller than wavelength, and the effective properties of this medium are hopefully able to provide a magnetic permeability. So what we need is to put these things together, and what Smith did it in 2001, 2000 with other scientists. There is this physical review letter paper in which they demonstrate that if you use wire medium with which has electric permittivity negative below the plasma frequency, below a certain frequency, which is called a plasma frequency, so the region blue. And if you use also, together with wire medium, this split ring resonator, which possess the negative permeability, no, in this region, the red region, and you are able to overlap, no, to let's say, engineer your material in order to overlap these regions, you are able to obtain negative refraction index material in a certain zone of frequency. So it's, as you see, is a certain limited frequency zone, but it was the first demonstration of these negative properties. This is the arrangement of the material, which is probably quite popular, in which you have a wire medium printed on the back side of a substrate in which you have a split ring resonator on the top side. And the material has been, let's say, replicated in order to form a three-dimensional medium. Okay, if you go a little bit on detail, if you have an electromagnetic wave with the electric field impinging on a wire medium with periodicity A and the wire and the radius to and the diameter, so radius R0 of the wires, what happens? You can, let's say, study the configuration with by putting some caps, so metallic caps on top and bottom, so as to form a parallel plate waveguide. It's easier to study this, and the parallel plate, let's say, acts like a boundary condition which replicates your material to the infinite. If you define the voltage of this material from the top side, from the bottom side at 0, Z at 0, and Z equal to D, you can define that the voltage is equal to the electric field EZ multiplied by D. No? It's the displacement of this field. It's voltage. So the voltage, if you see like an equivalent circuit, you can see that is the current flowing in this wire multiplied by the inductive component of this wire, so J omega L. So if you make the equalize these two relations, you obtain that the current in the wire E is equal to EZ divided by J omega L, where L is the inductance of this wire. So if you define the displacement field as dz along z like epsilon 0 minus sigma over omega multiplied by Ez, you can define that the polarization of the material introduced by the material is proportional to the surface current, so sigma to E divided by omega. So this is the polarization introduced by your material. The polarization Pz, the term Pz, as we said, is equal to J, which is sigma E, divided by J omega. If you replace your J with E divided by A square, which is the area of your unit cell, so the density of current is replicated by the current divided by the area, you obtain that, and you replicate the current E with this relation E, which we found before, you find that the polarization of this material is proportional to this relation. So we need to know the inductance of this wire. But anyway, you can define that D is displacement of the electric field, can be written in equivalent as a function of Ez, the external field. So we can define an effective permittivity for this medium, which clearly depend on the inductance of the wire. If we calculate the inductance of this wire, this wire array, by using the standard electrostatic principle, I will not have the time to repeat this calculation. You obtain that your effective permittivity can be written in this form. Let's say you have this the previous form in which I have replaced the inductance of this array of wires, which is the flux of the magnetic field divided by the current excited in the area of the unit cell, and I have replaced in the form. What we can see is that you can write your equation as a function of a certain Kp term. This Kp term is the cutoff wave number, and it will be also 2 pi over lambda p, which is the cutoff wavelength. What does it mean? It means that if you plot your permittivity, you have a behavior like this. So the real part of your permittivity along Z will have a negative behavior before a certain resonance. The resonance is defined as the plasma resonance. So this material behave as a plasma. Before this plasma frequency, you have a negative permittivity. After this plasma frequency, you have a plastic. So you have a sort of dielectric medium. But we are interested in this region where you have a negative permittivity. As you see, you can control the negative permittivity of your medium by playing with keeping fixed the periodicity of the medium. You can play with the radius of the wires to change your permittivity, negative permittivity. So you can engineer your material. The same, a similar approach can be followed for magnetic inclusions. So if you have a certain charge which is moved by an electric field, you produce a dipole moment. But if you move your electrons around a certain loop, you can produce a certain dipole moment M, which is proportional to the current flowing in this loop multiplied by the area of this loop, and the dipole moment is orthogonal to the loop. So this is similar to what determines the magnetic properties of ordinary material. There are a small loop of currents at atomic scale. In this case, we want to create or engineer this loop by using this split ring resonator. The idea is this one. Okay, if you take a loop and you cut this loop, you have this loop of current can be seen in this way with an equivalent circuit. You have this loop is very small. The area of this loop A, so the sides of the side is much smaller than wavelength as usual, and your loop has an inductive component determined by the current flowing on this wire. The inductance can be determined by using the standard theory of inductors, and you have a certain resistance because the current is flowing on a certain non-perfect conductor. And this gap, which we created in this loop, can create a certain capacitance in the circuit model. And the capacitance can be, in the first approximation, written as the capacitance of the parallel plate capacitor. So you can write that it's equal to epsilon 0, epsilon g, which is the epsilon r of the material put inside this gap. W is the width of your split ring. T is the width, and D is the distance of this gap. You have this equivalent circuit, so you can define that the current and the voltage in your equivalent circuit are related by this simple equation. So it's a series RLC circuit. So V is equal to R minus J over omega C plus J omega L multiplied by E. This is the impedance of the circuit, and this is the current. What we need to calculate is the magnetization induced by this magnetic dipole moments. So the magnetization is the magnetic dipole moment divided by the effective volume of your material. And as we said, the magnetic dipole moment induced by these loops is proportional to the current in the loops multiplied by the area, as we seen before. So the magnetization is the equivalent of the the electric polarization for magnetic material will induce magnetic properties. So an effective mu are different from the one of free space. So magnetization, we say that can be written as the current multiplied by the area. So at this point, I will replicate the current of the, I will replace the current of the equivalent circuit inside this formula. So V divided by impedance. So it's very simple substitution. Then I will use the Faraday law in order to say that the voltage in my circuit is proportional to the change of the flux in time with a negative sign. So the change of the flux in time of the magnetic flux is the H multiplied by A. So it's the magnetic field multiplied by the area. In the frequency, if I calculate in frequency, I introduce J omega, is the derivation of the, in time, it can be written as a J omega in a phasor domain. So I have that this is the Faraday law. So I want to replace V in my equation with this formula. So I introduce the magnetic field inside my magnetization is what I need to do. And so I put J omega mu 0 HA. At this point, I can write my mu r of my medium as 1 plus the susceptibility of magnetic susceptibility, which is 1 plus magnetization over mu 0 H. So my magnetization has been written as a function of H. It means that now I can write my term in simplifies H. I can now do this additional substitutions by using this parameter F and omega 0 as the 1 over L square root of LC and alpha as the R over L. And I can rewrite my formula in this more compact form. This is my magnetic, effective magnetic permeability of my medium, which is the behavior of this permeability. We can represent in this way. We see that we have this behavior. We have an increasing of the magnetic permeability up to a certain frequency, it's called resonance of my magnetic medium, which is 1 over LC, which LC are where LC are the parameter of my circuit model. And I have another resonance, which is called the plasma resonance of the magnetic medium, which is the frequency where the permeability of my medium goes to 0, equivalently to the model used for the effective permittivity. In this case, this is usually known as Lorentz model. The Lorentz model predicts that you have magnetic permeability inside a certain region of a frequency, which is between these two resonances, two frequencies, omega m0 and omega mp in the previous form. So this is the region of frequency where you can expect negative permeability. So if you change your inclusion, you can, let's say, if you use, you can use a split ring resonator, which is in this case the red curve. You can use even more compact particles. You can use a spiral resonator. Spiral resonator have the characteristic of having a resonance in a more compact region of space, which means that you can achieve your magnetic behavior in a region of frequency which is lower than split ring resonator. And this means that you have improved the compactness of the medium. It depends on the number of the turns of your split ring, of your spiral resonator. You can compact your medium or not. One of the main application which was proposed for this magnetic negative refraction medium was initially the perfect lens, the so-called perfect lens. The idea was to use this negative material inside between the two ordinary materials. So let's say air, negative permeability, negative effective index material, let's say -1, and air again. In this case, one could expect that the radiation is focused as a negative emitted by this source will be concentrated in a point inside the medium, and you can have another concentration outside from the medium, and this will produce a lens. What does a lens? And this was called the perfect lens because in principle has no problem with the diffraction limit, which is usually proportional to the wavelength of your electromagnetic wave. This is theoretically is a very good idea, but in practice is much more complicated to realize. Indeed, if you read papers in the literature, you are not finding probably a paper with very exciting results on this topic. The reason of the problem of this, let's say, fascinated applications, another very appealing application of this concept was the so-called cloaking, which was the idea to let the wave crossing a material without any scattering. And in this way, we were able to, let's say, obtain a certain mantle, which is producing visibility of objects. But in theory, it is possible to do this, but in practice, it's more difficult. The main difficulties to realize this medium are already evident, but I will underline a little bit more. The first problem is the spatial dispersion. The spatial dispersion means that the wave, the electromagnetic wave, should polarize it in a certain desired way in order to interact with this medium and produce negative refraction index. The condition is that you need to have the electric field aligned with the wires and the magnetic field coupled with the loops. This condition is guaranteed only if the wave direction is orthogonal with respect to the wire and orthogonal with respect to this loop. So you have in principle, you have just a single direction in which the properties of this medium are those that you were expecting. If you change the direction of your wave, you can expect very different behavior because the geometry of the material changes for the wave. It is polarization dependent. It's not really let's say a bulk material which has effective properties, because these effective properties are dependent on the wave direction. So if you change the wave direction, you have different properties. So you cannot simply define properties of a material without defining their behavior with respect to the angle. So you need, in this case, you need to define a certain tensor of permittivity, let's say, and permeability. You need to define in a Cartesian axis reference. You need to define epsilon x, epsilon y, epsilon z, mu x, mu y, and mu z, and maybe also the coupling terms between these mu x, y, and so on. You know, because maybe you have also coupling between x and y polarization. this is not really what was the initial objects of this material. So we need to maybe miniaturize a little bit more, or maybe we need more effective properties. So the other problem is the frequency dispersion, which means that the material properties are available in a small region of the frequency, and they are very rapidly changing. So if you change your frequency very small for a very limited change of resonance frequency, will dramatically change the properties of the material. And this is not very good from a practical point of view, because usually application of a certain bandwidth. So this means that you have these two main problems: frequency dispersion and the spatial dispersion, which has let's say limited the application of bulk metamaterials. This is probably why in the last period, if you search papers about metamaterial in literature, you usually find papers on metasurfaces, but very few on bulk metamaterial, because metasurfaces are much more the first reason for using metasurfaces that they are much more easy to produce. So you need just a lithographic process, and you can print on it very particles with every shape and every property, and you can even stack your surfaces in order to achieve properties which are enhanced. But these surfaces are much more, let's say, easy to handle with respect to bulk materials. For instance, you can design a lens. Really, you can really design a lens with the metasurfaces, not in principle, because if you let's say see this slide. You can, if you have a source located in P1, let's say in a source which is, let's say, radiating in a omnidirectional way, no, non-directive source, you can see that the radiated field as a summation of plane waves going in different directions. The idea of the flat lens is to use a metasurface which is characterized by different properties for different regions of space. In this case, you need to have, let's say, yellow particles that different from green particle or red particles, because yellow particle, if you write down formulas, you see that the delay of the wave to go from point 1 to point 2 passing through this path is subjected to a delay which is much larger than this path. So what we need to have, from this particle on the metasurface is to introduce a delay which is much smaller than the delay introduced by the red particle. If you write down all the contribution, you need to satisfy that all these paths have the same delay. If all these paths have the same delay, these plane waves, it will turn that the field radiated by point 1 will go directly in point 2, and you can decide which is the focus point of your lens depending on the properties of the lens itself. You can write this contribution, and in the end, you see that the condition that this particle need to satisfy is to have a variable delay. So it's a variable phase on the plane. You need to have also transmission magnitude equal to 1 for all these particles. So you need to control the phase, but at the same time you need to control the amplitude. This, in a more formal way, this property can be written as a generalized Snell law. Basically, if you write the Snell law, as we've seen before, from medium, we have ordinary medium, N1 and N2. So the strange medium is just the surface, which is not which does not introduce the same delay on all particles. You have different delay if you are moving on this direction. Basically, if you write down your Snell law without this term, is the conventional Snell law. But if you have at the interface a surface which is able to introduce an additional delay, you can modify the Snell law, which we have written before, in this way. So you can introduce this delta phase with respect to this direction x, divided by clearly k0, as we have done in the previous terms. It will go inside the equation, and this means that if you need to guarantee the conservation of the momentum at the interface, you can play with this delay, which is it's not an absolute delay. It's a delay with respect to the other particle, the other close particles. Is a gradual delay, so it's derivation of the derivative of the delay with respect to this direction. If you play with this parameter, you can change the angle of this electromagnetic wave propagating in the medium too. So we can play with the property of the surfaces, let's say metasurfaces. The gradient of the phase inside the surface will determine the bend of the wave in medium 2. These are interesting properties which has been used a lot in the literature. For instance, in this application, you can see a flat length which has been derived by using this particle, simple particle, which is patches. But they are distributed as you see in circles in order to obtain in a certain zone of the lens different property of phase. This surface is able to to focalize the field emitted by this horn antenna in the point F1, which is defined as the focus of the lens. If you see, for instance, if you call it the z-axis, if you see the plot of the field in the z-axis, you see that actually the field is much more concentrated, no? In this point with respect to the far field direction, which is usually the direction preferred by a standard antenna. So this is the field intensity of the black curve is the field intensity of the standard antenna, and this is the field intensity emitted with the lens. So as we see, by using metasurfaces, maybe multi-layer, we are able to synthesize the lenses, and this is a good thing. We can even design wideband lenses by using more complicated, particles. And as we said before, we need to guarantee also that the phase, you need to have a certain phase displacement between the elements, but at the same time, you need to transmit the field. You need to transmit the field completely. This is very good because you have these lenses can be also called free reflection lens, because as we see, we have that the transmitted field is 0 decibel, so you do not have any reflection at the interface, as it will happen with the shaped lens made of dielectric, usually used in optic application. This configuration allows also to synthesize tunable structures and you are able to, let's say, control, if you are able to control the phase of this element dynamically, so maybe through the polarization network and diodes or certain active components, they should be controlled, and you can design an electronically configurable transmit array, which is able to change, in this case, maybe the direction of the beam in far field, or maybe the focus point in near field. This is a dynamic lens, which is impossible to design with the classical lens approaches. So this antenna configuration is now very similar to a phased array configuration. This let's say flat lens concept has been used a lot from the group of Capasso, Harvard, and he basically used it for designing this metasurface optic lenses. Sorry. Okay. You say something? Oh. Okay. To see conventional optics, usually you need to design these bulk lenses with this profile, which is clearly very specifically controlled from with machines in order to design lenses. And in order to achieve a wideband operation, you need to stake several of these lenses. The idea is to use metasurfaces in optics also in order to reduce the profile of these lenses, because they you are able to, let's say, with the surfaces, maybe just a stake of a couple of surfaces to control the phase very specifically, and you are able also to guarantee the behavior of these lenses over different wavelengths. So these lenses are called no achromatic metasurfaces, because they work for different wavelengths. And if you need to have the behavior for different wavelengths guaranteed in conventional lens design, you need to guarantee several. You need to design this stake of lenses of elliptic and other shaped lenses in order to have this achromatic behavior. So you increase the profile of the lenses usually. So this application has been found much resonance in the media, and has been there were a patent which has been bought from Samsung some years ago for let's say I think €1 million. And a similar principle can be used to shape the beam of a certain electromagnetic wave, but in reflection. If you use, for instance, a metasurface, but with a ground plane, in this case is called artificial impedance surface, and you can focalize your field in a certain point in the reflection, or maybe you can do it for different frequencies. You can obtain different behavior for different frequencies, as we did in this paper. You can put, for instance, a different frequency. You can put the focal point in different points, or you can radiate different beams at different frequencies. And you can introduce polarization ability in your surface. So you have many degrees of freedom, because these cells are very manageable. You can use, as before, you can introduce tunability in these surfaces, in these reflection surfaces, and then you have in this paper of Steven Piper, you can see that if you control all the elements as before in reflection, you can control the beam direction or maybe also the focus direction. And this is the prototype of the reflect array or reflection metasurfaces. I can say some words about the synthesis of these metasurfaces. So we said, and then maybe we should conclude. I will not have the time to show you all the slides. And if you need to design a certain cell, no, for your configuration, the phase, you need to decide the phase and the amplitude of your cell. So maybe you need to design cell 1 with a certain amplitude and a certain phase, the cell 2 with another amplitude, with a similar amplitude and a different phase. How we can design it? So you can design with the approximate analysis, you can use equivalent circuit analysis, or you can use accurate analysis. Accurate analysis can be split in two. Let's say you can write your MOM code with the integral equation method, and it is very efficient, it's very rapid and very accurate, but it maybe is limited for the shapes, and you can handle only multi-layer surfaces or maybe single layer, and you cannot introduce bias. You do not have the same degrees of freedom of 3D electromagnetic software which are commercial, but it is much more efficient and more, let's say, accurate. I have worked a lot with equivalent circuit methods because they allows, so this is if you do a simulation, so you just introduce, you just design with your 3D CAD your unit cell, you put boundary condition and on the X and Y directions, so in order to have your unit cell to replicate it at infinite in the both direction, and you can put 2 ports on the bottom and top side of your cell, and you can calculate a reflection transmission coefficient both in amplitude and phase. If you this is a periodic boundaries. If you need to analyze your surfaces with an equivalent circuit method, you can let's say do something like that. You can represent your dielectric with the transmission line. You can represent your surfaces with a shunt impedance. You can decide the parameter of this shunt impedance. So in particular, the inductances and the capacitance. You need to find a model for this for your structures, for your bidimensional structure, or you need to derive from full wave simulation. It is very useful to do this exercise when you design a structure based on metasurfaces, because you understand very well the physics behind your structures, and you are able to, let's say, change the properties of your structure very easily once you have understood very well how where these strange properties came from. So if you decide to analyze your structure with equivalent circuit method, you need to take in mind this map. Let's say, as usual, if the periodicity of your unit cell is much smaller than wavelength, you can use the average theory. So maybe you can average the current on your surface in order to find a relation between the geometry parameter of your surface and the impedance. So what you need to have is the impedance of your surface. If the resonance, if you have a resonance region, so maybe your particle is resonating, you have a cross, you have a loop, you have other shapes which are resonating, maybe the periodicity is still smaller than wavelength, or maybe half wavelength is better. And you can still use the transmission line approach, but the properties of these shapes are not easy to find in analytic form. And you need to find a way to derive by yourself to retrieving approach from full wave simulation, and you use a method to derive your LC component. you have to pay attention to stay below this limit, because if you go in the region where the periodicity is larger than the wavelength, the effective wavelength, not the wavelength in free space, but the wavelength in the surface. Let's say if you have your surface embedded with the electric media, what is important is not the periodicity of the medium, but the periodicity multiplied by the effective epsilon r, square root of the effective epsilon r. So if you go beyond this limit, you have a multi-mode approach, and you cannot use the equivalent methods, because you have harmonics, you have many harmonics in propagation. So what happens if you have a periodic structures? You have the fields can be. This is an example of a periodic of a photonic crystal, but it happens similar things with the periodic structures. You can write down the field. You can see the field. The your periodic structure is periodic. So the amplitude of the field is periodic inside, and the periodicity is the periodicity of your medium. And you have the phase, so you have a certain amplitude, which is periodic, and a certain phase, which is the phase of your plane wave. So at the end, the field can be written as the term of the amplitude, which is a periodic function, and a certain phase. So you should use the Floquet theorem for these structures, and as we say, the field inside the structure can be defined as a periodic function for the amplitude and the certain phase term. So the periodic function can be expanded in harmonics, because as all the periodic function can be expanded as a summation of harmonics. So it means that if you expand the periodic function as a summation of harmonics, you obtain that your field can be written as a periodic function of x and y in your surface multiplied by a phase term. The phase term is now the propagation constant is now beta n, where beta is where n stays for the spatial harmonics. So you can have as many spatial harmonics as infinite. So you can have infinite spatial harmonics, and it depends if you excite them or not. So if the periodicity of your surface is smaller than the wavelength, you excite only the first harmonics. But if you have a periodicity which is larger than the wavelength, you excite more harmonics in your structures, and you are not able to analyze your structure with let's say single harmonics approach. This is the first harmonic, the frequency, the cutoff frequency of the first harmonic. If you have the first harmonic excited, so the wavelength is smaller than this quantity, you have grating lobes or harmonics excited. It means that if you have a wave coming from a direction, you do not have the wave going into the direction dictated by the Snell law only, but you can have additional propagation directions which are given by the harmonics contributions. Clearly, if you have a dielectrics close to your surface, you can define the so-called trapped grating lobes, which are harmonics, which are propagating close to the surface, but not in far field. So they are active only inside the medium, the electric medium inside the surface, very close to the surface. But they introduce nonlinear behavior as well. So for the circuit model, we prefer to stay below this limit. So with the circuit model, you can represent the wires for as an inductance if the field is aligned, or the wires as a capacitance if the field is aligned, is orthogonal to the capacitive strip grating. if you can define maybe patch or inductive filters, and you in this case you have both the inductance and capacitance in series. If you have the current flowing here, then it finds a gap which is a capacitor, and again an inductor, and so on. In this case, the current, the inductance and the capacitor are connected in parallel, so you have this equivalency. You can use even stranger shapes, and you can do a combination of shapes with respect to the classical elements. So you can design very strange unit cells. Even you can use also genetically optimized shapes with a certain pixelated region of space, and you can define very, very strange shapes. The important thing is to understand if it is really necessary or not to design these very strange shapes, because sometimes we see papers in which people use strange shapes, but sometimes they are not able to explain why they are using these strange shapes. Maybe the impedance is a very good method for the impedance medium, the retrieving of the impedance of these shapes is a very good very good approach for understanding if it is really necessary, the shape or not. Once you have your impedance, you can derive, let's say, for instance, if you have a inductive mesh filter or capacitive mesh filter, you can derive the impedance, effective impedance of the grid or the patches, and through the Babinet theorem, you derive the patches. And these are derived analytically and in analytic form. You can find the formulas in this paper as well. And that depends on the impinging angle also. So this is there is a spatial dispersion. But once you have the impedance, you are at a very good point for analyzing the structures, because you can write down the ABCD matrix of your system, and you use the impedance in the ABCD matrix, and then you can derive the reflection and transmission coefficient. Maybe, yeah, in this way. So maybe you have a wave, certain electromagnetic wave, you have the electric A surface and the electric B. You can write the global ABCD matrix by using the ABCD matrix of a standard transmission line, the ABCD matrix of the FSS, and the metasurface, and the transmission matrix of the second dielectrics. We have all this relation analytically available, so you can use this simple code to at least you analyze these structures at a preliminary stage. You can the analysis can work also at oblique instance. Clearly, if you do not have the impedance of your surface, you can use you can decide an equivalent circuit model for your shape, and then you take the reflection coefficient derived from full wave simulations and derive the impedance. As you have derived the impedance of your surface from full wave simulation, you can decide, you can find the values of LC component. We can do a couple of examples. For instance, if you use a patch array, standard patch array, the impedance is capacitive in the low frequency region, is very well matched by a capacitance, as predicted by the average model, which predicts only capacitive component. If you use the LC circuit representation, which is derived from full wave simulation, you can obtain a maybe more accurate representation of the impedance and the equivalent circuit. The equivalent LC representation is good also for crosses. For instance, if you use an array of crosses, you still have a capacitive behavior at low frequency, a certain resonance at a certain point, and then you have some strange behavior after this. Until up to the first resonance, at least, you can see that the behavior of your element is well matched by an LC series circuit. If you want to match the behavior of the impedance up to the grating lobe propagation, which is 30 gigahertz in this case, you need to use additional modes in your equivalent mode. This is the reflection coefficient derived from MOM simulation, the method with LC representation of the cross, which is very good representation up to 20 gigahertz, and with multi-mode representation, let's say, by including higher order mode. But if you include higher order mode, you complicate the circuit, and maybe it's more complicated to understand the physical reason of the behavior. So I suggest to stay to keep the things very simple. And if you analyze maybe another shape, which is the Jerusalem cross, you can see that if you complicate a little bit your equivalent circuit with the two parallel connections of LSC resonator, you see that you can match the behavior of your filter, of your reflection coefficient up to propagation of grating lobes. You predict the first resonance stop band, the pass band, and stop band again. Why? Because the first resonance at 11 gigahertz, you have a stop band due to the main cross. So this cross, this is the LC of the main part. The second resonance is determined by this additional segment, which determine the resonance at 29 gigahertz, as we can see from current distribution. And this is so the first resonance due to this part in the circuit mode, and the second resonance due to this additional part. When you introduce dielectrics, you need to change the capacitance of your surface, because the capacitance of your surface is influenced by let's say the element, the electric permittivity of the medium close to the surface. So you need to change a little bit the capacity to correct the capacitance, but you can, if you analyze the capacitance variation with respect to the periodicity of unit cell, you can see that if the electric medium is very thick around your periodic surface, you have that the permittivity, let's say effective permittivity of the medium, so the change in the capacitance is proportional to the real permittivity of the medium you put close to the FSS. If you have that the thickness of this additional dielectric medium is very small with respect to the periodicity, you have this transition function, which depends on the shape of the surface. You can maybe study also the behavior of the capacitance with respect to the incident angle, because as we said, you have a certain variation with respect to the incident angle depending on the different shapes. It's called the spatial dispersion, but this is the, let's say, improvement of the circuit model with respect to the normal incidents. And this is the approach if you want to use additional higher order modes. Let's say instead of using just an LC, you can introduce just two additional impedances, ZL and ZC, which take into account the effect of higher order modes, the capacitive modes and inductive modes, higher order. They are in cutoff, but they play an important role. So you can use this summation of modes for let's say matching the behavior of the wave propagation. It is a circuit model which is maybe useful to understand what is happening, but it is much more complicated. I will close the presentation here because I have no time to introduce the other application of Metasurfaces, but I have seen that you have many more talks about Metasurfaces in this course, so maybe you can have several interesting applications shown by other presenters. I will close the presentation here. I'm closing the presentation here because maybe I'm above 1 hour.
sir,
Thank you.
for nice presentation. We have learned many things from your presentation. Now, should I take the question?
Yes. I've seen
Sanjay sir, Sanjay sir, I have some clarifications in the slide. Can I go ahead? Some two slides.
Okay, okay, sir.
I can go ahead. Yeah?
Yes, sir. Sir, it is first thing is slide number 24.
Okay.
In that,
you want to ask about slide 24? Huh?
yes, sir.
Yeah.
What is L in that, sir? Small L.
The inductor is due to the current flowing on the split ring.
Okay, the small L is the perimeter.
Then
L is equal to mu naught A square divided by small L. You are given it, am I right?
yes.
What is that L, sir?
Sorry. L is the width of this wire. L. Sorry, I have to check in another presentation. Because I have removed some slides, maybe from another presentation I had. Usually, when you calculate the inductance of a solenoid, so L is defined as length of the solenoid in the case of solenoid. So in this case, it should be T. L should be T, actually.
Okay. L should be T.
It is a typo. It is a typo, sorry. Yes.
Yes, sir. Thank you. Another one is, one more is 29 slide, sir. Slide number 29.
Yes. Sorry, I have the wrong presentation of it. Okay, now it is
29.
Yes. Okay, 29 is this.
Yes, sir. Here, what is D minimum and what is L, sir? You made a D minimum as approximately L.
L is the wavelength.
L is the wavelength. Okay, thanks. Thank you, sir. Thank you for your nice presentation. And
yes, thank you. You have other questions?
Yeah, sir. Sir, in one of your slides, you use the spiral, and the number of spirals will lead to the change in frequency. What was that? You could add on the
Yeah. Maybe this one.
Yes, sir. Exactly.
Yes, if you increase the number of turns in the spiral, N stays for the number of turns of the spiral. So if you do 1 turn, 2 turns, and 5 turns, you have more length of the wire. You have a smaller resonance frequency.
Okay.
Sir, my question is in terms of periodicity and
Sir,
thickness.
taking the question. So we are taking the questions on the chat box.
Okay, how we differentiate between metamaterial and metasurface in terms of periodicity and thickness?
No, the difference, I think, in terms of periodicity, the objective is the same, is to keep the periodicity as small as possible. Actually, in metasurfaces, it is quite possible because you find many papers in which the periodicity, you find applications in which the periodicity is in the order of 1/10 of the wavelength. You find very good applications in which you can control the phase of metasurfaces elements even if the periodicity is much smaller than wavelength. And in this case, you can really use homogenization of the surface. And if you use, let's say, equivalent method with effective theory on effective impedance for analyzing the structures, you can see that they match very well with the full wave results. It means that the effective effective impedance approach work quite well. So with respect to the periodicity, the idea is the same. In metamaterial, is maybe more difficult to achieve the properties independent of in a wide band. In metasurfaces, the important thing is the impedance. And as you can see, you can achieve very wide band and stable reflection coefficient or phases, phase response by using metasurfaces. In metamaterials, since you want to use let's say this principle of a negative refraction index, you need to work in a region of frequency which is very small, and the properties of the material are very rapidly varying, because you need to match two conditions, both the electric permittivity negative and magnetic permeability negative, and this is a very let's say stringent condition, no, for achieving the desired properties. And this is probably the problem of these metamaterials. In addition to that, also the thickness, as you said, no, in metamaterials, the idea is to create a bulk medium. So you want to create a certain homogeneous material which is has a certain thickness, no. You cannot simply, sometimes we see that people use effective permittivity and effective permeability to represent surfaces, but actually for surfaces the best approach is to use the susceptibility or impedance, no, is the best concept, because instead, if you use bulk material, you need to use effective permeability and effective permittivity. So I think in terms of thickness, metasurfaces are thought to be thin, no? In metamaterials are another game. They want to. The idea is to have a very bulk medium, no? If you think to photonic crystal, for instance, also photonic crystal are a bulk medium, and in this case, you need to design a three-dimensional structures, maybe to confine light. No, the main idea is to confine light in a very small portion of space, no, in order to have this very appealing application for even quantum computing or something, you know. So the objective, I think, is a little bit different, no, but the idea to homogenize the surface or the material is the same.
Okay, so the next question is, how can we enhance the evanescent? Same, how can we detect it?
How we can
enhance the evanescent?
The evanescence. How we can enhance the evanescence, the evanescence. So how we can? I didn't understand very well the question. How we can enhance the evanescence? Maybe it was referred. Maybe it was referred to a precise slide. I don't remember the slide where in spiral, maybe it was referred to.
Starting, sir. In this skill.
This slide, or maybe here. I don't remember. But in general, evanescent fields, maybe if it is referred to evanescent fields, let's say you can you need to have as usual the fields can be expanded in harmonics. So if the harmonics are propagate, let's say a little bit far from the surface, you have that the evanescent field propagate a little bit more or less depending on the properties of the material. So you need to study the propagation constant, the attenuation constant of the evanescent field. It can be, let's say, also studied in detail by using dispersion diagram or other approaches.
So next question is.
Okay. Okay, how the transmission reflection can be controlled? Maybe for metasurfaces. Yeah, they can be controlled by using by selecting the correct shape. Let's say if we select, let's say, as in this case, we can control the amplitude and the phase. We need to select a shape of your unit cell in order to control the reflection coefficient. For instance, if you use this is a simple example of patches, we see that for patches you can control the amplitude. No, it's a low pass filter. A patch filter is a low pass, so you can have impedance. When the impedance is 0, you have a total reflection. When the impedance is very high, you have total transmission. So you can select the element which is characterized by the impedance behavior, which allows you to determine to have the total transmission, but also the correct phase that if you want to design the metasurface lens and so on. Okay, the next I'm reading about in the chat. A transmission and reflection phase can be controlled, and what property can change for that? As we said, yes, you need to control the shape of this of the elements. For instance, if you change shape, crosses, you can have a different behavior of the reflection transmission coefficient and clearly different behavior on the phase. But another idea is to stack more of this layer. No, if you put not just one layer of patches, but you can put, for instance, patches, grid, and patches. And if you study the system of these 3 layers together, so you can see maybe the thickness is a little bit increased, but you can shape and you have much more degrees of freedom in controlling the phase of your unit cell device. There are some papers about this transmit arrays and so on. Difference between metasurface and metamaterial, maybe we are already discussed. How we can calculate the equivalent circuit model of double square split ring resonator. I suggest to calculate the circuit model of a single split ring resonator to run a simulation with because we can maybe say, okay, in my opinion is a series RLC, but a method which is much more reliable is to run a simulation of this shape, maybe without dielectrics. Then you take the reflection and transmission coefficient by using this model of transmission line model. So let's say IR impedance and IR, you can derive the impedance of your split ring if you see the behavior of the impedance, you actually see what is the equivalent circuit you need for matching, because if you have just a single resonance, you need, like this, you need a series RLC. If you have another behavior like inductive impedance in the low region and then it becomes capacitive after the resonance, you need the parallel LC. So you can decide the shape of your circuit also by helping yourself with the simulation and the calculation of the impedance. How we can apply spectral domain method to metamaterials? Yeah, spectral domain methods, I don't know what you mean, but maybe you mean also the MOM integral equation can be written in the spectral domains, actually resolving in the spectral domain. We can use, let's say, spectral domain, so the transformer domain for solving the metamaterial for sure, because we have a representation of the field in terms of harmonics, and it is very, very, very useful. Which metastructures gives wideband response? Okay, metastructure. Actually, the shapes giving the most wideband response are those simple, because if you have patches or grids are the most widebands. If you need, but sometimes you need more than wideband and you need to use stranger shapes. But if you just need wideband, the regular shapes are the best ones. Is the formula to calculate the reflection transmission phase? Is there any formula to calculate the reflection and transmission? For sure, you can, when you calculate the reflection coefficient from the ABCD approach, you have the ABCD matrix, you calculate ABCD matrix, then you take the relation between the S parameter and the ABCD matrix. You can find on Pozar book, on the other books. Maybe I didn't report here, but they are very simple relations. You can translate your ABCD matrix into S parameters, and S parameter are complex number, and you can find phase and amplitude. How to calculate the distance between the structure in the metasurface? The distance between the structure, let's say maybe the periodicity. The periodicity is a degree of freedom. As we said, we should keep it not too large to avoid the propagation of higher order harmonics. So maybe you can even have the propagation higher order harmonics, but if you need them, sometimes people there are papers of people studying the scattering, diffusion, and so on. In this case, you can maybe use the scattering harmonics, but if you just need to have the first harmonic, you should keep the period quite small respect to wavelength. What happens if the modulated patches in FSS are arranged in a regular spatial variation will produce multiband or wideband? If arranged in a regular spatial variation, okay, if you have patches which are regular, let's say periodic, you just derive this behavior, which is a spatial filter, which with the periodic distribution of patches, it is not periodic. But when you need to design metasurface lens, what the hypothesis we usually do is that you have a local periodicity. So you have each unit cell is studied as if it were in a periodic fashion configuration. So you study the single unit cells as periodic. Then you take the reflection transmission coefficient and you can use as a building block also of an aperiodic structure. For obtaining multiband, I think the best way to obtaining multiband is to use more fancy shape, not patches. For instance, we used this one for designing multiband reflector array, but there are other ones, and it's not the only one. for instance, this shape, no? You have the first loop, which was used for high frequency, and the stubs are used for controlling the phase. If you change the length of the stubs, you control the phase. Central loop is for the second frequency, the third loop for the low band frequency, this one. So we have first, second, and third frequency. We are able to change the phase independently in all three frequencies, and we can design this multi-band structure. Modulated patches in a unit cell. Yes, you can use modulated patches. Let's say once you have studied the structures separately, you can use modulated surface by using what you have learned from the periodic analysis. In many papers, return loss has been calculated using input impedance. How we can calculate the transmission loss? Yeah, for calculating the transmission loss, you should use the ABCD approach. ABCD approach is very useful method for computing the whole scattering matrix, because if you, as you said, if you use just the input impedance, you can calculate the reflection coefficient, but not the transmission coefficient. On the contrary, if you use the ABCD matrix and you translate the ABCD matrix in a scattering parameter, as we discussed, by using the relation between the scattering parameters and the ABCD matrix, which is, you can find, I say, in Pozza's book, for instance, or maybe in papers I wrote in the past. You find both the reflection and transmission coefficient, and you are able to calculate also the transmission loss. Okay, slide 61. 61, if the metal is increased in terms of shape form, 61. 61. Maybe I've gone a little bit fast on this. If the metal is increased in different shape form, millimeter, what's changed in terms of performance? Okay, this slide represents the effective permittivity variation with respect to the thickness of the layer D, which is the small d, and D, the capital D, is the periodicity of the unit cell. So what is important in FSS is not the thickness of the layer in absolute value, but is the thickness of the layer of the electric with respect to the periodicity of the medium of the surface. If this quantity is larger, no? It's let's say larger than 0.3, you can have that your effective permittivity used in the circuit model is basically the same of the dielectrics. If the thickness of the layer is much smaller than the periodicity of the surface, so you are using thin layers, the effective permittivity is actually more closer to the higher permittivity, which is because it's a certain averaging of the permittivity between higher and the electrics, if you have thin dielectrics around the FSS. The shape of the surface influences this transition function. I found that actually, if you have this filling factor increased, this transition function, these are curves derived directly from MOM simulation. So you can see that if you increase the filling factor, you always obtain the same behavior, but with a different transition function. Okay. Thank you.
Sir, I have a question.
Yes. Yes.
My question is, sir,
Yeah.
suppose I propose a equivalent circuit.
I'm not able to hear.
No.
Maybe you can write the question. Yeah. Yeah, the equivalent circuit. I have the yeah. The equivalent parameters.
equivalent circuit parameter.
How we can derive the equivalent circuit parameters? Yeah, you can match. For instance, if you
Yes.
need, if you need to compute the LC, no, for this impedance behavior. Let us assume you have the red curve you have derived from a MOM simulation, no? You have that your equivalent circuit, you have to select, you have decided that the LC circuit is good for matching this impedance, because we see also we see that this behavior that can be matched by an equivalent LC circuit. But how much, how the LC should be for matching? Actually, you can run, you can take, you can write in a MATLAB code, no? You impose that at the resonance frequency, the impedance, no, is going to 0. So when the impedance is 0, the relation between the inductance and capacitance is null, no? Because it depends on the resonance frequency. You can run an optimization, say, or a cycle in MATLAB for deciding which is the best inductance, which satisfies the resonance at these points, which matches your impedance behavior. Once you have done this simple routine in MATLAB, you can derive the L and C values for this specific shape, no? And this can be repeated for all the shapes, no? You have a very it's a very general approach, no? It's valid for all the shapes. Okay.
Okay, thank you,
Vice
Professor
President.
Costa,
Yeah.
for such a nice lecture. And now I invite Professor Somawa Mukherjee, who is the Vice Chairman of IEEE Rajasthan subsection, to present the vote of thanks to Professor Costa.
Okay, thank you. Thank you.
Yes, it was a very good presentation, Professor Costa, and I sincerely thank you for showing each individual methods to calculate the parameters. That is very crucial, and I am very sure that all the participants has been got very good idea how to analyze these metamaterial unit cells. And I sincerely thank you for your time. And seeing the enthusiasm of the participants, I hope that we will organize more events with you. Probably we have actually 3 student branch of IEEE Antenna Society in IEEE Rajasthan subsection. One is in IIT Jaipur, and other 2 are in Manipal and Ajmer College. And we are sure that we will be organizing more events like this. We are hoping that you will be able to deliver more such interesting lecture. So thank you, Professor Costa.
Thank you. I will stop sharing my screen. Okay.
Yeah, sure.
Thank you.
Thank you.
Thank
you for your hospitality.
Yeah, thank you, Professor Costa. On behalf of IEEE Rajasthan subsection, IEEE APS chapter Jaipur, MNIT Jaipur, and Government Women Engineering Jaipur, I thank you for such a vibrant talk. And I think all the questions has been answered, as well as we have learned many things about the metamaterials for the DNG, SRR, metasurfaces. You have covered so many topics here in only 1 hour.
Yes, maybe I had another 50 slides, but it was really too long.
Yeah, I have given researchers so much of work that they can research on that.
Okay, thank you.
Yeah. Okay, thank you. And so just thank you for just answering my mails so quickly, because I just made easily he accepted for the lecture.
Yeah. Rajesh, maybe say that he's your friend, no? Rajesh.
Yeah.
He's a postdoc. He's a postdoc in our department.
Yeah.
Okay. Thank you. I stopped my video as well.
Okay. Thank you, sir. Okay, thank you, Somawa, sir.
Thank you.
Okay, participants, meet you tomorrow morning in the next session of the third day of the workshop. Okay, thank you everyone. Okay, thank you, Somava sir. I think we should stop.
Thank you. Thank you. Bye.
Bye.